There's 3 different graphs that they want you to know what they look like, and I'm sure you've seen them before in other classes. You'll see them in chemistry. I think I've seen them in Orgo, so I've seen them there. I've definitely seen them in the general chem class, so that's a requirement for you, right? I didn't say some happy things just now, did I? So what does y equals e to the x look like? Y equals e to the x. You can graph it. On your calculator, it should look like a EXP button. So let me see what it looks like here. If in doubt, you can always, yeah, here it is. It's the shift function of ln, natural log. So it looks like this. It starts at 1, and it just explodes like this. Where do you get that? You see those kind of graphs all the time. And I'm drawing it only in the first quadrant because I'm an applied mathematician. And usually the x-axis is time, and the y-axis is something I'm graphing. So populations grow like this. Bacteria grows like this. So they're exponential functions. Fleas grow like this. So many of the microbes that you're looking at, I don't know do you guys do stuff like this in biolab? You look at things that grow cells. Cell division grows like this. So if you ever culture cells in a, do you do that experiment? Culture cells inside a petri dish, and then do you weigh them? Or how do you know how much is in there? So you look at area on the plate. Is that what you do? So that if you graph the area on the plate as a function of time, this is the picture you're going to get. And if in doubt, you can always plot it on your calculator to make sure. But that's why that particular function is really important. Your Webassign has it like this, but usually you see it like this, e to the minus x. E to the minus x is super important too, because it's what we call a saturation function. It usually doesn't flow like this. I'll give you an example in a second. That graph looks like this. It saturates down to 0. And we see combinations of this. Probably when I went upstairs to chemistry and asked them, what do you need students to know? And I asked biology, what do you need students to know for our math classes? They said dose-response equations. So dose-response equations are a combination of these kind of functions, which is not on your Webassign, but is super important. Another function they seem to want you to know, which is not, I don't think is as important, is e to the 1 over x. So e to the 1 over x looks like, well, it has an asymptote. Looks like this. So you can separate out the 3 graphs. You'll be able to answer that question easily. So I have some beautiful examples of where this is used. It doesn't level off at 0. These examples, most things don't. So it's not, you're not really going to get e to the minus x. You're going to get e to the minus x leveled off at something. One example I can give you is body temperature. I'm not into forensic science. I actually use that only for teaching. But you can imagine that if someone actually passed away and you were able to record their body temperature at time of death, and let's say you found them over time, like 1 hour after, you would expect that their temperature would go down. But their temperature wouldn't keep going down forever as a line, which is probably what you do in bio classes. You fit your equations with lines, right? You take the data and put a line through it. One of the major criticisms of medicine, that you take data and then put a line through it. Not everything's a line. This idea of body temperature going down after time of death is not a line. What should happen? If it was a line, what would happen? Would the body freeze according to the line? According to the line, if it was a line. Yes, it would, right? It would just keep going down, 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 and it would never stop. What do you expect should happen? Let's suppose someone died in here of boredom, and we didn't know it. We came back. The next day, would they be frozen? No. What temperature do you expect if you put your hand on their body? What temperature would you expect it to be at? Go ahead, say it. You're thinking it. Would they be frozen? What temperature do you think they would be? I asked you about this in Richardson Hall. Room temperature of Richardson Hall. They would not go below the room temperature of Richardson Hall. So that's why we call that saturation. They would level off. In chemistry, we call it thermal equilibrium. They would not go below the room temperature. So it wouldn't level off at 0, but it would level off at room temperature. So this function is used all the time to talk about things that saturate or go down to an equilibrium. There's other combinations of these functions that I see all the time. Here's one I saw, very interesting, done by medical people. So they looked at people, how they eat. They made a little scale, and they watched how much food comes off the plate, how fast it comes off the plate. So I can just look at the grams of food that comes off the plate and total it up over time. And so what you'd expect to see is that you'd see this graph going up, right? They're eating, and as they're cleaning up their plate, more and more food goes in their body. So these grams of foods it's going up. Initially you have very little, and then it goes up like this. What they noticed is when the lean people ate, it looked like a line. So they graphed it, it looked like this. They started out at 0, and they went up like this. But when the obese ate, they didn't look like that. They looked like this. Right? So when I looked at these graphs for the first time, what I noticed first is that the obese ate longer than the lean. That's the first thing. So what they did is they said this guy, for lean people it's a line, for obese people they said it's a quadratic, because a quadratic curves like that. Parabolas curve like that. But as a mathematician I asked myself, well, shouldn't parabolas go down? They go up and then they go down. They have a maximal point and then they go down, right? Upside down bucket. Would someone's food coming off their plate ever go down? Unless they're throwing up, it's not going to go down, right? The food coming off their plates, the amount of food they've consumed is always going to go up. It has nowhere else to go. So this is not actually quadratic. What's probably happening is this. Saturation. That's probably what's happening. They're going to eat the food, and they're going to put less and less in their body as time goes on because they're getting full. Right? So it's never going to go down like a parabola. It's probably going to level off. And lean people are probably on the same graph. They probably eat for less time. But I bet if you took a bunch of lean people, I want to run this experiment actually. Take a bunch of lean people and have them eat at a pie eating contest. I bet you they also would do this. Right? And these curves have certain numbers in them. You can normalize everybody under those numbers and compare one person to the other. Not line versus parabola, but one curve with the same numbers, and that would tell me if you're a different eater than you. I could look at your numbers and look at her numbers and see if you guys are eating differently. That's really what needs to be done. And I did that. And guess what? The obese aren't eating differently than the lean. They're just eating longer. That's what's going on. It's very interesting where these curves come up. They come up all the time. Dirk Vanderklein, I don't know if any of you had him as a professor yet. He gave me some of his data to look at. Again, it was exponentials. They're all over the place. So this kind of stuff you're going to see again. Come on, he's a good professor.